Our topic today is state of charge estimation. State of charge measures the amount of energy available in a battery at a specific time, and it's normally expressed in percentage. In automotive industry, we use gauging to predict the amount of energy available in a battery pack. The gauge we use must be very sophisticated to keep us in track with the range and the available energy available to us. If that gauge is not correct, well, what happens is bad. Is basically we are stranded on the road, and we don't want to be in that situation. Therefore, state of charge use very sophisticated algorithm and consider the following operations, like minimum and maximum voltage threshold, minimum and maximum temperature, battery degradation due to aging or cycling, and battery self-discharging due to internal resistors. In an ideal world, a battery should provide, when the load is applied, the exact voltage that is rated at. So, for example, this battery is rated for 12 volts. It should provide a 12 volts at the load. As you see, the curve is flat, and it just basically the battery dies when there is no more energy in it. But that's the ideal world. In the real world, normally the battery have some kind of internal resistors, and when you have an internal resistor, there will be an internal voltage drop, and that's what explains basically the voltage is not flat like before, like the red one, and it's more like the white curve, as you see here, which is not linear. In the beginning, there is a sharp drop of voltage, and there is some kind of you can resemble this as an RC circuit, and then towards the end there is a non-linear drop, and all of a sudden a sharp drop voltage. So this is the real scenario when we have an internal resistor. So the voltage applied at the load is less than the voltage of the battery because of this internal resistance. Let's look at the voltage response of a battery after discharge. When the system is on, the cell voltage, when the system is on, there is a drop voltage in the beginning, and then there is a force regime, as I mentioned before. You can compare this to, for example, this blue part as a resistance in series, and then this red part here as an RC resistor, if you want to think of that. After the discharge and the system is off, it will be some kind of relaxation time, but before that relaxation, we will have a voltage drop, just like in the beginning here, due to that RS or the series resistor, and a relaxation time where the voltage is going through relaxation and stabilization. So it's after this stabilization that takes hours. Luckily for the automotive industry, car stays overnight charging, and it takes a long time before we can measure that OCV or open circuit voltage. It's during this time where we can actually get accurate measurements, because at this time the voltage is still stabilizing here, and then it gets to a point where, like after a few hours, when we can actually read an actual or correct voltage, and we call this OCV or open circuit voltage. There are multiple methods of estimating state of charge. there is a direct voltage measurement. Coulomb counting, so basically the state of charge is calculated using current integration divided by a total capacity. Kalman filter and a neural network method. In direct voltage measurement, we measure the voltage using the open circuit voltage method, as I mentioned before. An open circuit voltage state of charge table is basically calculated during measurement, and we can see, for example, this table we have for every voltage entry based on the temperature. So here is like 20 degrees, here is minus 20 degree. We can see the values. So the lower the temperature, at very low temperature, you can see the state of charge is less than what we have at an ambient temperature, for example. The voltage-based method first measure the open circuit voltage and then estimate the state of charge by looking up the OCV, SOC, or the open circuit voltage state of charge table. However, these methods cannot perform well for lithium-ion battery because of their non-stationary nature and the discharge process. Coulomb counting, basically this method using current integration by measuring the current using either a shunt resistor or some kind of Hall effect, or using some kind of Hall effect sensor. The state of charge is calculated using this formula here during lapse of time, where C represents the total capacity and I is nothing but the current. In the Coulomb counting, the state of charge value is obtained by integrating the current on the time axis. Although the Coulomb counting is easy to calculate, the measurement and computation error are accumulated during the integration process, and the state of charge initial value is not easily obtained. Kalman filter is a recursive algorithm that continuously predicts future states based on observations. Using measured data from voltage and current and estimated voltage, temperature, Kalman filter use all these measured data, voltage, temperature, and current, and fuse it with the model that is created based on RC circuits, like shown here, to predict the state of charge at any specific moment. The last algorithm is neural network, where voltage, current, data are used in a neural network to basically predict the state of charge. A large set of data combined from voltage, current, and temperature are used, trained, tested, and validated with the neural network to predict the actual state of charge at any moment. Thank you.